Okay, let's go ahead and work through this homework problem. We have a ball with a mass of 0.2 kilograms moving with a velocity of 1.5 meters per second in the positive x direction. So let's go ahead and just make a little sketch here. Reduce our font here. It's moving in this direction with 0.2 kilograms. And there is another mass with 0.3 kilograms moving in this direction with a velocity of 0.4 meters per second in the negative direction, so it's moving this way. This one has 1.5 meters per second. Now, this is an elastic collision, which means that afterwards they're going to be moving with their individual velocities. And this is a bit of a tricky question because we have two unknowns, the velocity of the first mass and the velocity of the second mass after the collision. So whereas normally we try and ask you to go ahead and work in variables for as long as you can, if you do that, you will just end up deriving those two big long equations that are in the textbook that I told you you don't really have to use. So rather than do that, basically do a whole derivation, in this case we're going to go ahead and work this problem with where we plug in some numbers. I'm not going to completely plug in numbers. Here's what I'm going to do. We have conservation of mass, conservation of momentum, sorry. Conservation of momentum. So we're going to write that down, right? So the condition before is that we have m1 v1 plus m2 v2 has to equal the momentum afterwards, which would be m1 times v1, and I'm going to call after, I'm just going to give it a prime, plus m2 v2 prime, right, where the primes mean afterwards. And the masses stay the same before and after, so we don't have to give them primes. We're going to combine this with the relative velocity equation. I didn't want to make a circle there. Okay, so let me see if I can put a big box around this. This is our conservation of momentum equation. And we're going to do the relative velocity equation, which is that v1 minus v2 in the initial state, right, that's that relative velocity, put little parentheses around here, is equal to minus the relative velocity in the final state, which is v1 prime minus v2 prime. All right? And what we're going to do is we're going to realize that because we have v1 and v2, right, v1 and v2, right, we'll give these proper labels here. We'll make this m1, give this m2. This is a number, okay? v1 minus v2, it's 0.9, right? Actually, sorry, this is, let's make it explicit, this is minus because it's moving in this direction. So v1 minus v2, which is in a minus sign, is actually 1.9, right? This is 1.5 minus 0.4 meters per second, right? Which is equal to 1.9 meters per second. Okay, so they're approaching each other at 1.9 meters per second. But I'm just going to write that as a pound sign, number. Okay, so what this tells us is that we can write sorry, what we're going to do is we're going to write v2 prime in terms of v1 prime. v2 prime is equal to, you know what, I'm going to back up for a second. I'm going to expand the right half of here. Right. So this is minus v1. I'm going to bring the minus sign inside, and that makes it plus v2 prime. Minus v1 prime plus v2 prime is equal to number, right? Is equal to just a number, which is 1.9. All right, so let me go ahead and scoot this up a little bit. Let's continue going. All right, so this, therefore, I can now write v2 prime in terms of v1 prime. v2 prime, keeping it on the left-hand side, is just equal to number plus v1 prime. Right? Okay. So that's, given that we know the initial velocities, this is what our relative velocity equation boils down to. Now we can look up here at our conservation of momentum equation, and what we can do is we can plug in this v2 prime into that equation right there. Okay, so let's do it. Give myself some writing room here. We can now write conservation of momentum as m1 v1 plus m2 v2 is equal to m1 v1 prime plus, and now we'll substitute in, we have m2 times v2 prime, but v2 prime is now just a number, that's 1.9, plus v1 prime. Okay, so now we have an equation in terms of the knowns. This is known, this is known, m1 is known, m2 is known, number is a known quantity, and we just have one unknown, v1 prime, right? So we're going to isolate v1 prime because that's the thing we're trying to solve for. So we'll expand this out a little bit. I'm going to move this up now that we've substituted that in. We're going to start with this, which we got from substituting in our relative velocity equation into our conservation momentum equation. Let me rewrite the right-hand side a little bit. That's going to be, that's a very poor equal sign. So that's going to be equal to m1 v1 prime plus m2 times a number, and that was our 1.9, plus m2 times v1 prime. All right, just distributing the m2. Okay, so then what we can do is we're going to pull the v1 primes together. That's equal to m1 v1 prime plus m2 v1 prime plus m2 times number. And we can rewrite this as m1 plus m2 all times v1 prime plus m2 times number. All right, and that's of course equal to, on the left-hand side here, m1 v1 plus m2 v2. Okay, so now we want to solve for v1, right? So we'll pull that on the, we'll flip these sides. We'll say m1 plus m2 times v1 prime is equal to this, and we'll bring this onto the other side, right? So we'll say m1 v1 plus m2 v2 minus m2 number. Okay, which finally gives us v1 prime is equal to this whole thing, m1 v1 plus m2 v2 minus m2 times, get that little thing there, m2 times number, all over m1 plus m2. And now we can just plug in our value for m1, our value for v1, our value for m2, our value for v2, our value for m2, and our value for the relative velocity. If we go back up and look, remember that our number was 1.5 minus 0.5, or 0.4 was equal to 1.9 meters per second. Right. So this number here was 1.9 meters per second. If we do that, we figure out v1 prime, and I think once you have that, the rest of it's pretty straightforward, because now you can go back to your original equation for conservation of momentum up here, and once you have m1 v1 prime and you have m2, you can solve for v2 prime, right? And you can go from there. All right, so that is how you solve that problem. Now, for those of you who are interested, I will actually show you the, you can stop now if you want, but this will effectively show you what would happen if we actually work this out symbolically. We would start with m1 v1 plus m2 v2 is equal to m1 v1 prime plus m2 v2 prime. I'm actually going to make this a little bit larger for us, make the writing a little easier. Okay. Then we would take the relative velocity equation, which is that v1 minus v2 is equal to minus v1 prime minus v2 prime, and rewrite this as v1 minus v2 is equal to minus v1 prime plus v2 prime, just pulling the minus sign inside the parentheses, right? So that we get v2 prime is equal to v1 minus v2 plus v1 prime. Right? So if we keep everything in symbols and we don't plug in a number like we did before, then when we get to our conservation of momentum equation, we can take this symbolic equation and plug it in for v2 prime here, and that becomes m1 v1 plus m2 v2 is equal to m1 v1 prime plus m2, and this becomes v2 prime is now v1 minus v2 plus v1 prime. Right, and now we can collect the v1 primes. Right, so this is equal to m1. There's an m2 v1 prime here, so I'll pull that out, plus m2 v1 prime plus what's left over, m2 v1 plus m2 v2. Actually, this is a minus, because that's a minus sign right there. So we're going to erase this a little bit and replace it with a minus. Minus. So there's this term, there's that term, and this term came over here on this side. Okay? So then we have So now we're going to collect, we're going to get this term by itself. So we're going to say m1 plus m2 v1 prime is equal to, what's on this side, m1 v1 plus m2 v2. And then from this we subtract off these two terms here. So we have minus m2 v1 and then minus minus, so this becomes plus m2 v2. Okay? And you see here we have m2 v2 over here, and we have m2 v2 over here. So we can combine those. That's equal to m1 v1 minus m2 v1 plus 2 m2 v2. But you see here we've got v1 in each term here, so we can write this as m1 minus m2. Clean that up a tiny bit. m1 minus m2 times v1 plus 2m2 v2. And that's all equal to m1 plus m2 v1 prime. Right? So now, finally, we can take v1 prime is equal to this whole thing divided by m1 plus m2. Right? And I'm going to be lazy, and I'm just going to copy all this directly here. Right? Divide this term by m1 plus m2, and divide this term by m1 plus m2. And lo and behold, if you go back and look into the textbook, this is exactly that big nasty equation that I told you about. And we just derived it, right? So we could have worked completely symbolically, but we would have ended up with this equation, and then we could just plug in our numbers, right? Since a little easier way was what we did, which was to go ahead and plug in numbers. I didn't actually plug in 1.9, I just left it as a number symbol, but you could plug in 1.9, put in other numbers like the masses in, and calculate it a little more straightforwardly, okay? So either way works.